Okay, looking at question 3 of these worked solutions, we're told here snow avalanches can be a problem for travelers, yada yada. A very common type of avalanche is called a slab avalanche, and they have been studied extensively in Canada. Slab avalanches in Canada have an average thickness of 67 centimeters. Ski Patrol in Vail, Colorado is studying slab avalanches in their region. A random sample of avalanches in the spring gave thicknesses found in a data file called. Okay, so in this data file, which we'll go into in a minute, we have some information of slab avalanche thicknesses in Colorado. Question is, use a 1% level of significance to determine whether slab avalanches in Colorado are different from those in the Canadian Rockies. Now we are basically being asked to make a decision about slab avalanches in Colorado, and we want to compare that population to a population mean of 67. Okay, so we know the average thickness of these types of avalanches in Canada is 67. Is the average in Colorado the same, or is it different? Basically is the question. Now, by the way, notice that this question does not tell me to determine whether it's the mean of these slab avalanches, but really we are being asked to compare to Colorado to the Canadian Rockies, and the value in the question is about the average thickness. So I would infer from that that I need to compare the average in Colorado. Okay, we're not being asked to do a confidence interval, and really there's only two ways, at least in this course, that we're going to make decisions about populations. We either calculate confidence intervals or we do a test of hypothesis. In this case, it's going to be a test of hypothesis. Okay, any test of hypothesis, you basically have to do 5 things. You've got to specify a null hypothesis, an alternate, you've got to calculate a test statistic. Based on your test statistic, you get a p-value, which is a probability, and then you're going to make your conclusion. Well, all right, your null statement is always something about a population parameter, and a population parameter we're interested in is the average. And we want to know, is the average in Canada, is the average slab thickness in Colorado the same as it is in Canada? So if it turns out that my data support the null hypothesis, H naught, I'm going to conclude that the average thickness of these avalanches, average thickness in Colorado is the same as in Canada. That's basically what it's going to come down to. If I could spell Canada, that would be fine, but I don't care. All right, so if it's this, the average thickness is the same. The question, however, that I'm really looking for is whether they're different. So if they're different, and my question doesn't say, it doesn't ask me whether they're thicker or whether they're thinner, it just says, are they different? In which case, the average thickness won't be equal to 67. So if it comes down to this one, the average, AVG, average thickness in Colorado is not the same as in Canada. That's what it rolls out to. Now, good practice. I always do this. I put my level of significance right under my hypotheses. We are told to make a decision at a 1% level of significance. Now, that is the error that we are allowing ourselves to make. And by the way, that represents the probability of me committing a type 1 error. A type 1 error is when I reject the null hypothesis when I should not be doing that. And as a researcher, I set this value myself, and it has been decided that we're going to use a 1% level of significance, and you always express that alpha value as a decimal. Okay, we have to calculate a test statistic. The test statistic we calculate is dependent on the test that we are using. Going forward in this course, we're going to find out that there's 2 tests you can use to test population means. There's something called the one sample Z and the one sample T, and we are not getting into T's at this moment because T's are used when you have small samples. So this one's going to be the Z. Now, before I can go calculate the Z, I need to go and get some data out of my Minitab. So I'm going to go to Minitab over here. I've got the data here. And by the way, we have 66 data points, and we were not told in the problem the true population standard deviation, that is the sigma value. But because our sample size is over 60 or 60 or more, I am allowed to use the sample standard deviation. So that's what I'm going to do here. And in order to do the calculation by hand, I need some summary statistics. So I've gone into, hang on, now let me do that again because I did that kind of fast. Stat, basic statistics, display my descriptive stats. And I want Minitab to give me some descriptive stats. I need to know how many avalanches were measured, what was the sample average, and I need to know the sample standard deviation. By the way, Minitab also gives me the standard error of the mean, which we'll see pop up at 1.78, at least I think. All right, now, so I have this information. Knowing that information, I would then go calculate my test statistic, which I have already done. And I'm going to put it right here. Yep, here it is. Okay, so it's a Z. When I calculate a Z, and that Z is associated with population mean, here's the formula. It says, go get a sample, calculate your sample mean. All right. From the Minitab printout I just had, the mean of my sample was 59.95, and I want to find out what is the difference between the sample mean and the mean in my statement of claim, and my statement is that the mean is equal to 67. That's the value that gets popped in here. Now normally we would be dividing by population standard deviation, which we don't know, but because our sample size is over 60 or 60 or over, we're allowed to substitute the sample standard deviation. I plug that in, and here's the value. I divide by square root of n, and I get a test statistic of negative 3.95. So that's my test statistic. I'm going to use this value to find the area under the curve, and the area under the curve represents my p-value, which actually is a probability. Now, normally, if you were going to do this kind of a question without the aid of software, you would go to your normal distribution tables and you'd find areas, in this case, to the left of negative 3.95, and you'd have to multiply it by 2. The reason for that is because our alternate statement says not equal to. That means we have to consider situations where the mean may be greater than 67 and where it may be less than 67. So if I was working this one out by hand, and I'm going to cheat a bit here and I'm going to use my Minitab, I could get the area under the curve, which is my p-value, using my probability distribution plot. View my probability. I'm dealing with the standard normal Z distribution. Mean is 0, standard deviation is 1. I'm going to give it a Z score. The Z score is minus 3.95, and I want it to give me the area in both tails because this is a two-tailed test. So my p-value actually represents this area plus this one right here, and because this curve is symmetric, I can take either one of these and multiply by 2 in order to get my p-value. And in actual fact, while I'm at this now, I'm gonna copy this baby and put it over in my sheet. I'll just leave that there for a minute. Okay, now let's go back to our Word document and let's see about calculating the p-value, which I already have done. And let me copy and paste that. Okay, wherever it went, here it is. There's my p-value, and what does p represent? Okay, well, p, first of all, is the probability that z could be greater than 3.95, or I could have written this as less than minus 3.95, but it doesn't matter. I choose either the upper tail area or the lower tail area, and I got to multiply by 2. So that's what's going on here. Here's my total p-value. And if I bring this thing up here, hang on now. Trying to get the formatting right. My p-value actually represents these two tail areas right here. Okay, so I've got that done. Now, I didn't ask it in this question, but I will fix the question afterwards. I should also go to Minitab and see what Minitab does for me. So let's get Minitab to give us the answer without us having to do any hand calculation whatsoever. We go to the Stat tab, Basic Statistics, and we are using a one sample Z. We're doing, and this thing will either do a test of hypothesis or give you a confidence interval or do both. Right now we want a test of hypothesis. Now we have raw data, so if I stick my cursor in here, any raw data I have will pop up. It wants to know the known standard deviation. It's looking for population standard deviation, but we don't know that, but we're allowed to plug in sample standard deviation because our sample size is 60 or more. Now, we indicate the hypothesized mean, which in this case is 67. We go to options. We want to know, is our mean not equal to the 67? And as for the confidence level, you don't have to change this. You really only need to worry about this if you're going to answer the question based on a confidence interval. So I'll throw this in anyway. We had a 1% level of significance. Level of significance is risk. So if I got a 1% risk, I'm going to have a 99% confidence. Say OK and OK. All right, and I'm going to copy and paste this into my Word file so that we can compare what we got from Minitab and what we get from hand calculation. So coming back in here again. All right, I calculated negative 3.95. What does Minitab give me? It gives me the negative 3.95, tells me it calculated a Z. Okay, and have a look at what Minitab has written up here just to make sure you got it right. We wanted to know, is the mean equal to 67 versus is it not equal to 67? We've given it the sample standard deviation to use in the calculation. All right, and it gives me a p-value. Now, unfortunately, Minitab rounds our p-values off to 3 places after the decimal, so I'm only getting an approximate value. This is the actual value right here. But I kind of really only need to know the relative size of this p-value. All right, I've done the test, I've got it in Minitab, and now the decision. The decision is always, your decision is based on this question. Is your p-value less than or possibly equal to your alpha value? Now, if I use the value from Minitab, Minitab gave me 0.000. Is that value less than my level of alpha, which is 0.01? Well, clearly, something that's on the order of magnitude of 0.001 is smaller than 0.01. The answer to this question is yes. Anytime the answer is yes, you are always going to reject your null hypothesis. Okay, great. I'm rejecting my null hypothesis. So what does this mean in the context of my problem? My data are telling me to reject this statement. This statement is not likely to be true. And is this right? Well, let's just have a look here for a second. We want to know, are the Colorado avalanches, do they have a thickness of 67 or is it different than 67? When we look at our data showed a sample mean of approximately 60, Well, 60 is a smaller number than 67. Question, of course, is whether it is significantly smaller than 67. And the statistics are saying that yes, it is. That's the probability, and you are comparing that p-value to alpha. This number, or if I want to be more correct, this one right here, these are smaller numbers than this one. Anytime that happens, you're going to reject the null hypothesis, and that means the data are more supportive of this statement right here. So what am I going to conclude? I'm really going to conclude that my test results show me that the average thickness of the Colorado slab avalanches is not the same as it is in Canada. Now, how do I want to phrase that? Well, there's all kinds of ways I could phrase that, and I'm going to show you probably a more complete answer than many textbooks might do. First of all, when you write your conclusion, you should tell your reader what test did you perform. We performed a one sample Z test. You usually tell your reader what your test statistic was equal to, and you give your reader your p-value. Now, if I use Minitab, it's going to come up as 0.00, which doesn't mean too much. Some textbooks, by the way, will say p is less than 0.0001. Because you don't know what it is, you just know that it's less than. Anyway, I know my exact p-value, so I can do that. All right, results of my test conclude that the average thickness of slab avalanches in the region of Vail, Colorado, and I give my reader some summary statistics from my sample, is significantly different from the thickness of slab avalanches in the Rocky Mountains of Canada, which are on average 67 centimeters thick. So ultimately, what am I deciding? My avalanches in Colorado are different from the thickness in Canada. Now, something else I could have a look at, and this comes up in your assignment, is this thing right here. This gives me more information than the test of hypothesis. The test of hypothesis simply says, my data support this statement, or this one, whichever way you're looking at it. It's saying that they're not equal to 67, but the p-value doesn't tell me if they're bigger or smaller than 67. This confidence interval, however, does tell me that they're smaller. How come? Because all the numbers in this interval from 55.35 to 64.54, all of these numbers are smaller than 65. So really what the confidence interval tells me is that the average thickness of slab avalanches in Vail, Colorado are in fact not as thick, or they're thinner, than they are in the Canadian Rockies. Okay, that's a mouthful.